All right, guys, we had some homework on page 37 last night, question 1 and 2. Any issues with either of those questions, 1 and 2 on page 37? Do we need to go over one of them or both of them? Really? None? We're good with both of them? All right. We also had our constant speed and velocity worksheet that was due today. 4 questions on it. The answers are up on the board right now. Any issues with any of those 4 questions from our worksheet? Yeah, absolutely. Number 3 is the one with the kilometers per hour and seconds thing, isn't it? Yeah. Lewis? Yeah. Meters per second, I don't have that answer in meters per second. It would be okay to do that. I'm thinking the answer in meters per second would be 17, let me think here, 3, yeah, it would be about that, yeah, so that sounds about right. You go what? 46. Oh, you calculated the displacement. Let's take a look at number 4 though as well. Okay, so we had an issue with it, so let's take a look at it, and we'll take a look at number 3. 3 is probably the toughest question on the page, so we'll do both of those. All right, number 3 first. 3 says the average braking time for a driver, which is the time between when the driver recognizes that he needs to stop until the time that he actually applies his foot on the brake, was found in a 2001 study to be 2.3 seconds. So in other words, we're not counting the time that the car skids here. We're just simply counting the time that it takes for the driver to react to whatever's in front of him. Okay, 2.3 seconds. So driving down the road, oh, there's something on the road. I should put my foot on the brake. 2.3 seconds later, his or her foot is actually on the brake. How far does he travel during that time between when he recognizes that there's a problem on the road and he actually puts the foot on the brake to begin to stop? All right, we've got a couple givens here. We've got a time of 2.3 seconds. And we've got a velocity here. We'll define north as positive. We've got a velocity here of 90.0 kilometers per hour. We want to find the displacement. So on the surface, it might seem like a relatively straightforward question. The equation that we have that describes constant velocity is displacement over time. We can rearrange that, multiply both sides by time, and it ends up looking something like this. D is equal to V times T. But we have a problem here in that we don't have consistent units. We've got seconds for time, and then we've got kilometers per hour for velocity. Seconds would be fine. Hours would be fine. But we have to be consistent. We can't use both. It's either got to be seconds or hours. Now, right now, I think for you, the easiest way to do this is to convert the seconds to hours. Okay, but after we're done doing that, I'm going to show you how to convert kilometers per hour to meters per second. That's a little bit of a tougher conversion. So we'll do the seconds to hours first. How do we convert seconds to minutes? How many seconds in a minute? Lewis? 60, good. How many minutes in an hour? 60. So if we want to convert seconds to minutes, we're going to divide by 60. If we want to convert minutes to hours, we're going to divide by 60. So we're going to take this 2.3, we're going to divide it by 60, we're going to divide it by 60 again to get hours. And what do we end up getting there when we do that? I don't have all my work shown on this page, so I don't know what that is in hours. 6.38 times 10 to the negative 4 hours. We know it's going to be a really, really small number, right? Because 2.3 seconds is a really, really short time. That's a tiny fraction of an hour. So now we can multiply 90 kilometers per hour by 6.38 times 10 to the negative 4 hours. We can do that because we've got consistent units now, right? We're in hours for both of them. When we do that math, it works out to be, I actually get 0.0575. Wait a sec, I told you the answer was 57.5, didn't I? Well, what is that units? 0.0575 what? kilometers, right? We're using kilometers per hour. My answer's got to be in kilometers. You can leave it that way if you want, or I just divided it by 1,000 and get 57.5 meters. So either one of those would be a correct answer. Now, I'm going to show you a little trick for converting kilometers per hour to meters per second here. When we converted seconds to hours, there was one unit to convert, right? Seconds to hours. Divide it by 60 and then 60 again. In the end, we divide it by 3,600 because there's 3,600 seconds in an hour. But when we're converting kilometers per hour to meters per second, there's two units to convert. There's kilometers to meters, and then there's hours to seconds, right? Kilometers per hour to meters per second. Kilometers has to be converted, and hours has to be converted. So let's do that. 90 kilometers per hour. Let's do one of them at a time. How many meters in an hour again? Sorry, how many meters in a kilometer again? 1,000. So on the top, we would say 90,000 meters per hour, right? We've just converted one of those units. We've converted kilometers to meters. We still have hours on the bottom because we haven't done anything with that. 90,000 meters on the top. Well, now let's convert hours to seconds. How many seconds in an hour? Looks? Sorry? Yeah, 3,600 because there's 60 seconds in a minute and then 60 minutes in an hour. So it's 3,600 seconds in an hour, right? 90,000 meters in 90 kilometers, 3,600 seconds in 1 hour. So 90,000 divided by 3,600 gives me 25. What are my units that are left over? Meters and seconds. So it's not crazy hard. You just got to recognize that it's two conversions instead of one. Instead of just dividing by 3,600 like we did up here, we've got to multiply by 1,000 and then divide it by 3,600 so that we can convert both of those things, kilometers and hours. Is that okay? Now, once we get that 25 meters per second, we could go back and do this question a different way. D is equal to V times T. The velocity here is 25 meters per second times a time of 2.3 seconds. What do you think we get when we multiply 25 by 2.3? 57.5. Right? So it doesn't matter which way you do it. They're both correct. Okay, I just picked up here the way that I thought was a little bit easier because we only had to do one conversion instead of two. Did anybody, just out of curiosity, okay, this is the way that I would expect those of you who got the question correct to have done it, but did anybody do it this way? Good. Good for you guys. Did you get it right? Excellent. And that's a tough unit conversion to do if you've never seen it before, right? If I haven't taught it to you before. So good for you. All right, number 4 was the other one we needed to go over. It says downtown Calgary is 61 kilometers north of High River, while Okotoks is 15 kilometers north of High River. You drive from Okotoks to downtown Calgary in a time of 45 minutes. What's your average velocity? Downtown Calgary is 61 kilometers north of High River. Is that a distance? Is that a position? Or is that a displacement? Is that where Calgary is? Or is that how far Calgary's gone? That's position, right? We're going to say north is positive. Question number 4. Everything's north in this question, so we might as well make north positive. We're going to say D1, position 1. No, we're going from Okotoks to Calgary. So the final position is 61 kilometers, right? My initial position, Okotoks, is 15 kilometers north of High River. Let's not call that D2 and D1, though. Let's call it DI and DF, right? My initial position, my final position. My initial position was Okotoks. Okotoks is here, not Okotoks has traveled this far. Calgary is here, 61 kilometers north of High River. The time that it takes was 45 minutes. That time, would that be a that be a T or a delta T? If you look at your watch, that's T. Is that the 45 minutes that we're talking about? Stephanie? No, so it's going to be delta T? Yes, good. It's a time interval, right? All right, let's say that V is equal to delta D over delta T. Oh, okay. Can we do 61 minus 45? That gives me 46 kilometers divided by 45 minutes. Can we do that? Is that okay to do it? You know what it is? It's odd. What are we going to get for an answer there? 1 point something? What would the units be? Kilometers per minute. That's an odd set of units. It's right. If you did that on a test, I'd mark that right. But it's just an odd set of units. I've never even heard anybody use kilometers per minute before. Okay, so we're probably going to do a conversion here so that we don't have to have an answer in kilometers per minute. What I did, in fact, is converted this minutes into hours by dividing by 60. And when I did that, I ended up getting 61.3 kilometers per hour. Okay, that's correct. So was whatever answer we would have gotten in kilometers per minute, also correct. Now, some of you did meters per second. Okay, let's look at that one. If we're doing meters per second, then the displacement isn't 46 kilometers. The displacement would be 46,000 meters. And the time isn't 45 minutes. The time would be 2,700 seconds. Is that right? And when we divide 46,000 meters by 2,700 seconds, we get, what was it, 17 point something, did you guys say? 14? 17 even? Okay, so both are right. Okay, if you specify what units you're using, kilometers per hour, meters per second, kilometers per minute for that matter, we'll mark it right. Okay, you don't have to have it in the units that I expect you to do it in. You just have to have it correct. Any questions about either of those questions or any of the other two questions on that page? The first one was 70.0 kilometers per hour or 19.4 meters per second. Either one. And 2 was 1.08 times 10 to the 12 meters. Or I could have said, I suppose, 1.08 times 10 to the 9 kilometers. Okay? All right, what I'd like you to do right now, please, is just flip the page over and right now at your seats, do question number 5. If you finish that up really, really quickly, then do number 6 as well. But I just want to make sure that you guys are okay with number 5 before I go and assign number 6 with you, okay? I'll give you about 4 or 5 minutes to do that one now. All right, everyone, let's take a look at question number 5 now from the back of that worksheet. It says a jogger runs 5 kilometers north in 25 minutes, then stops for a break for 10 minutes, then runs 10 kilometers south in 53 meters. What's the average speed and the average velocity? So what we want to do here is kind of just take a step back from the question for a second and not just automatically write down givens, but just think about what's going on in this question. Okay? The jogger is running north. Then the jogger takes a break. Then the jogger runs south. That's really like 3 problems. Like that's 3 different things, right? 3 different events that are taking place. So let's consider our givens from that perspective. In stage 1, the jogger runs 5 kilometers north. We're going to make north positive again. The jogger runs 5 kilometers north in stage 1. In a time of 21 minutes, or 25 minutes, I should say. I'm actually going to call that D1, and I'm going to call that T1 for displacement in the first stage, the time of the first stage. In the second stage, Stephanie, in the second stage, what do we have here? A brake, right? So my displacement in the second stage would be what? Right? Not moving, right? Kilometers, meters, whatever you want to put it in, because 0 is 0. But we do have a time in the second stage because that person took a break for a defined time of 10 minutes. In the third stage, we also have a displacement. Looks like 10 kilometers again. And we have a time here of, what do we got, 53 minutes. Is that right? Is that right? Let me tell you a little, give you a little hint here. Things to watch out for down the road. Stephanie's caught it, I think, here. I'll ask her in just a second what she was going to say, but I think she's caught the little hint that I threw at you. Sometimes I do this. Sometimes when I ask you if that's it, and sometimes when I leave a space before a number, it means there's supposed to be something there before that number. Stephanie? Should be negative, yeah. I left a space for the negative, right? I left it off on purpose to see if you guys catch that. Stephanie did. Okay, why is it supposed to be negative, Stephanie? Good. Don't south. Right? We could have defined south as positive and then made that positive 10. But if we had done that, then north would have been negative, and that would have been negative 5, right? It doesn't really matter as long as you specify. All right. Now here's the temptation of people. V equals d over t for this one. V equals d over t for this one. V equals d over t for this one. Add them up, divide by 3, right? Average them out. That doesn't work. We've got to find the average displacement, the average velocity. We've got to take the total displacement over the total time. Now the total displacement here would be negative 5 kilometers. 5 plus 0 plus negative 10. Add them up, right? We subtract positions, we add displacements. Add them up. The time here, what is that, 35 minutes, 88 minutes, is it? Is it 88 minutes? Well, we got to figure that out in hours, probably. We could use it in minutes, I guess. 88 minutes. 5 divided by 88 gives me whatever velocity I get in kilometers per minute. I don't want to do that, I don't think, though. Let's go kilometers per hour. 88 minutes is what? 88 divided by 60 is, yeah, 1.46 hours. And what's 5 divided by 1.46? About 3.5-ish. 3.4? 3.42, thank you. We're actually going to round that to two digits. So if we go back to our original data, it's 2 digits, right? Neg 3.4 kilometers per hour. Negative because it's south, right? Oh, wait a second. Wait a second. What have I just found? What have I just found? We were asked to find 2 things, average speed and average velocity. What have I just found? I found the average velocity. I was asked to find speed first, then velocity. It doesn't matter that I got velocity first, okay, as long as I recognize that's what it is. Okay, this is the average velocity. Average speed, on the other hand, we don't have to write down our givens again. The average speed is simply distance over time. The distance would be 5 plus 0 plus 10, 15. Because we're not paying attention to the direction here now, right? Okay, I don't care that I went 10 to the south. I just care that I went 10. The direction doesn't matter. Yeah. Good question. I'll check that in just a second. Okay, I don't know. I don't have that on my sheet here, but I'll check that in just a second. Okay. So we got a time here that's still the same, 1.46 hours. 15 divided by 1.46. That gave me 10.2. We're going to round that to 2 digits, or 10 kilometers per hour. Good. Zane just asked a good question about meters per second. What would this be in meters per second? I'll figure out, give me 2 seconds, I'll figure out what that is in meters per second here. Now keep in mind that these are rounded numbers, so the number I'm going to give you isn't exactly what you would have gotten because you used unrounded numbers through your calculations there, but you'll see if you're right or not at least. First one's going to be somewhere around 0.94, negative 0.94, and the second one will be somewhere around 2.7, 2.8. Okay. Was there a hand up back here somewhere? Yeah, Tony? Good question. Somebody else asked that question earlier too. So when we're getting speed and velocity, we use the time, we included the time when the person was stopped. Why do we do that when we're finding the average speed? Well, I told you guys on the first day when I gave you that example of driving across the country and getting to Regina and seeing that sign 750 kilometers to Calgary. In my mind, okay, not my physics mind, but just my driver mind. We've all done this, right? We see a sign 750 kilometers. We're thinking, okay, how long is that going to take me to get there? 7.5-ish hours, right? Even before you learn physics, you think like, okay, an 800-kilometer trip is about 8 hours, right? We can average about 100 kilometers per hour. But if I stop in Moose Jaw for a couple of hours, then all of a sudden, I'm not going to average 100 kilometers per hour. Okay? It's going to take me longer than 8 hours because I can't average as much when I'm stopped. Give you another example. Driving to Edmonton. Edmonton's a little bit more than this, but let's say it's 300 kilometers. Okay, let's say it normally takes you 3 hours. Okay, what's your average speed there? You averaged 100 kilometers per hour, right? So let's say you're driving to Edmonton and you stop in Red Deer for an hour. Now it's taking you 4 hours. We don't say our average speed is 100 kilometers per hour, right? Intuitively, we know that our average speed was less than that. It took us 4 hours to go 300 kilometers. It wasn't 100 kilometers per hour. Why? Because we stopped. When we have that average speed in there of less than 100 kilometers per hour, we took into account the time that we were stopped for. So in that case, it would be 75 kilometers per hour we would have averaged. All in all, when you're finding average velocity or average speed, you include an entire trip, the entire distance or displacement for the entire trip, and the entire time for the entire trip. Now, displacement in stage 2 was 0, so that was a non-factor. The time wasn't, so we have to include that. Okay, is that okay? How many people didn't include the time for the second one? Okay, that would probably be a fairly common mistake, actually, I would think. Tony, if you ever had a question like that on a test and it was multiple choice, what do you think one of the options would be? Yeah, probably whatever you get when you don't include that, right? So we got to be careful of that, right? Okay, we good? All right, let's do question number 6 for homework, okay? I'm not going to give you a chance to work on that right now. Just do it over the weekend for homework. We'll take a peek at it on Monday. Right now, we're going to shift gears a little bit and take a look at some graphs. There are many, many graphs that we can see in Physics 20, the first of which is what we call a position time graph. A position time graph is a graph that has position on the y-axis and time on the x-axis. The title of a graph will always be y versus x. That's why we call this position versus time, or position time, as opposed to time position. Okay, it's always going to be whatever's on the y-axis versus whatever's on the x-axis, position time. The one that's on the y-axis will always be our responding variable, and whatever's on the x-axis will always be our manipulated variable. Do you guys remember the difference between a manipulated and responding variable? Manipulated is what you're changing. Responding is what happens because of that. So it's always going to be y versus x, or responding versus manipulated. In this case, our graphs are position versus time. So position is on the y-axis, time is on the x-axis. Time would be the manipulated variable, and position would be the responding variable. Now, each of these graphs show data for position versus time, but they show 5 different shapes. What I want to do right now is go through what each of these shapes mean. And I want you to know them, but I don't want you to memorize them. I don't want you to remember them. I want you to think every time you see a graph, what does this mean? Because you understand the shape of the graph. In this first graph here, let's not even pay any attention to the other ones. Let's just look at the first one here. We've got a straight line on a position time graph. Okay? Straight line on a position time graph. This graph represents how far you're going, how much the position changes by in a certain amount of time. What do you think it represents? What do you think this line on the graph represents there? Good. It's moving at a certain speed or velocity. It'd be velocity in this case because it's position as opposed to distance. Okay, so it'd be velocity as opposed to speed, but close. Okay. The rate of change of position is velocity. So this line represents velocity. But because it's a constant line or a straight line, it's a constant velocity. The speed isn't changing. So we're going to write in here that this is a constant velocity. You're driving to Edmonton, you set your cruise control on 108 kilometers per hour, you stay there at 108 kilometers per hour the whole time. Now this is position versus time. We still see a line on a position versus time. The line, by the way, on a position versus time will always represent something about velocity, something to do with velocity. Because position time, the rate of change of position is velocity. Specifically, what velocity are we talking about here in this graph, where we have a straight line, but it's flat? Dan, are you ready to raise your hand there? Zero velocity. In other words, it's stopped. You could say it's stopped, or you could say it's a constant velocity of 0, or just not moving, anything like that, right? Right, look at it. The position isn't changing. If this is position red deer, and this is position red deer, and this is position red deer, and this is position red deer, because it hasn't changed, well, then your velocity is 0. You're stopped in red deer. Here's another one, also a straight line, but this time it's sloped downwards instead of upwards. No, close. That would be the first guess of a lot of people, I think. Yes, yes. It's a constant negative velocity. Now let me explain exactly what that means. The constant negative velocity. This doesn't mean necessarily that we're driving in reverse. Okay, if we drive to Edmonton in reverse, that doesn't make it a constant negative velocity. If we define north as positive, then driving to Edmonton in forward or reverse is still at positive velocity, and we'd still graph it like this. Okay, constant negative velocity means you're going in the negative direction. You're going at a constant speed, not necessarily backwards in your car or walking backwards or whatever. You're just going in the negative direction. Okay, if I define the back of the room as positive, right now I have a positive velocity. Right now I have a negative velocity. Even though I'm walking forward, I'm walking towards the front of the room. Okay, it's a negative velocity. Right now, if that's positive, this is a positive velocity. Okay, right now, hey, that direction is negative. This is a negative velocity. It doesn't matter which way you're facing. What matters is which way you're moving with your frame of reference here. So constant negative velocity, you're going at a constant velocity, but you're going in the negative direction. Oh boy. Don't like these ones when you start seeing curved ones. Anybody want to take a stab at this one? It's going faster. Look, the slope is increasing. If we take a look at a real brief moment in time right here, the displacement over here is very, very small during that moment in time. Let's take a look at an equal time interval over here. Okay, still the same time interval, right? But my displacement is much greater right here. If my displacement was a little bit here and a lot right here, then I must be speeding up. What's another word for speeding up? Acceleration. So if I gave you this on a quiz or a test, if you said acceleration, that'd be fine. If you said speeding up, that'd be fine. Anything like that would be fine. We got one more here. One more. This one would be slowing down. Yeah. Slope is decreasing here, so this one is decelerating. Slowing down. Decreasing velocity, you might say. Okay, I'm going to give you another one that's not on here. Here's a tough one. Let's see if you can do this one. Still position versus time. Oh boy. Who thinks they're smart enough to tackle this one? You're at a curved line, but it's curving a different way. Carrie? Okay, so accelerating, it kind of looks like he's accelerating in this stage, right? And then he's turning around and slowing down. Good guess, but not right. Nobody else? Okay. Okay, so accelerating in this phase, then turning around and then accelerating the other way. Okay, good guess, but not right. Carry again. Oh, decelerates, slowing down, stops, and then turns around and accelerates. Nope. Okay, so it starts to move constant speed and goes faster. Nope, good guess, but nope. Nope. Not in so many words. You'll see what I mean by that in a second. Oh my goodness. Nobody's got it yet. Louis? Yeah, I mean, it's a trick, right? It can't happen. Because what's he really doing? He's accelerating, and then all of a sudden, time stops. He doesn't stop. Time stops. And then what does he do? He's going back in time. He's not going backwards. He's going back in time, right? Which obviously we can't do, right? I'll never give you that on a test, guys. I'll never give you that on a test because it's an impossibility. I just wanted to see if you could, remember I said, I don't want you to memorize what each of these things mean. I want you to be able to figure out based on shapes what things mean, based on logic what things mean. I just wanted to see if you could figure out that that can't happen because it means going back in time, okay? Let's give you one more, actually. How about this one? He's not going back in time here. Yeah. Yeah, so he's moving, but time isn't elapsing, right? So that's an impossibility as well, unless you're somehow outside of time. Unless you're God and you're outside of time, this graph is impossible. So I wouldn't give you that one on a test either, okay? I'm sorry? No, that's a good comment. Light, but it's not right. Light travels at about 1 billion kilometers per hour. I mean, that's fast, right? To give you some perspective there, Canada is about 6,000 kilometers wide. If you turned on a flashlight in Halifax and you had a mirror in Victoria and then another mirror in Halifax, and let's assume that that flashlight, the light from that flashlight could bounce back and forth between Halifax and Victoria. It couldn't, right? It couldn't because of the curvature of the Earth and because the light would dissipate long before it ever made it that far. But let's pretend that it could. it would make about 25 or 30 return trips, Halifax, Victoria, and back again. 25 or 30 return trips in 1 second. That's how fast light travels. So it's very, very fast, but it's not instantaneous. That means that time still goes by. So if you saw a graph of light speed, it would still be this graph. It would just have a really, really steep slope. That's all, because it's a really, really high velocity. Does that make sense? Okay, a steep slope, but not an infinite slope or an undefined slope, whatever you call that. Okay, does that make sense? All right. So it's not just a matter of for us of determining what a graph means, although that's important. It's also a matter of us determining some numbers from a position time graph. We're going to do one little thing here, and then we'll wrap it up for the day, and we'll pick this up on Monday. Monday or Tuesday, we'll do a little activity with this. Get a position time graph here. And I want to find just a nice, straightforward position time graph that looks like this. And I want to find the position at a specific moment in time. In other words, where the object is now or later on. Okay, I want to find the position at a specific moment in time. Let's say this time right here, 5 seconds. How do I do that? Derek, how do I do that? No? Yep. Yeah, just go up and over. There's the position at that time. Up and over. Yep. Okay, let me come back to that a little bit later if we have some time, okay? Good question, but we'll come back to it. What about displacement on a position time graph? How did we define displacement again? It's been, what, 4 days now since we defined it the first time? What is displacement? It is the change in position. All right, we just got position. How are we going to get displacement? The change in position. Yeah, just two positions and subtract them. It's up and over again, then subtract them. In other words, the displacement is the final position minus the initial position, which we learned about that. Just not in the context of a graph, right? The average velocity on a position time graph. Average velocity. There's two ways you can do this, although they end up being the exact same thing. It's just a different way of thinking. The average velocity, when we did our problems over the last couple of days, was displacement over time. Did we just not learn how to find displacement on the graph? Up and over, subtract the two, there's displacement. And then the time you read off the x-axis. That's one way to think of it. The other way to think of the velocity, of finding the average velocity, is the slope of the graph. You guys remember how to find slope of the graph? Rise over run. Look at what the rise is. The rise is the change in position, displacement. Look at what the run is, the change in time. So what does the slope really work out to be? Delta D over delta T. Think of it either way. I don't care. They both work out to be the same thing, the same answer. Okay? One more thing. Hold on. The instantaneous velocity on a position time graph. Instantaneous means not the average, what you're moving on average between here and Edmonton. The instantaneous means what's the velocity now or now or now. Look, this is a straight line. This is a straight line. If you want to find the velocity on a straight line, we know that it's constant. If the average velocity between here and here is let's say 15 meters per second, but it's a constant velocity, then what's the instantaneous velocity going to be here or here or here or here? It's the same. If it's a constant velocity, if it's constant, the instantaneous has to be the same as the average. So I'm just going to say same as average if it's a straight line. Now, if it's not a straight line, all bets are off there, and I'll show you how to do that next week, okay? Have a good weekend, guys. Remember, your homework this weekend is question number 6 on that worksheet, and we may just have ourselves a little quiz on Monday. Maybe. So let's be ready for that on Monday, okay? Not on this stuff, just on the position, displacement, velocity, and so on, okay? Have a good weekend, guys.